Welcome back, folks. So today we're going to build a new module, another module for our look at modular design. And the module I want to build here is something to help me out with our end project, the project I have in mind. Now, for that project, I want to use a small 8-pin microcontroller. So I don't have a lot of pins to play with. And I already have to run a display. I have to be able to beep a buzzer. And I need input, and I think I need 4 switches. So this is my idea. What I'm going to do is create an analog keyboard. And little schematic here that I sketched up. If you look at it, it's just a voltage divider, really. So we've got down here, we've got the bottom resistor, R1, we'll call that. Got a little bit of capacitor across it here to stabilize it a bit. And as I plunk down these switches, I want, either 100% of VCC, 75%, 50%, 25%, something I can look at with an analog to digital converter pin on the microcontroller and decide which switch has been pressed down. And that way I only need one pin. If we look quickly here at our voltage divider formula, so we just rearrange that a little bit, and we come out here that RA, that's RA is up here, is equal to R1 over X minus R1, where X is that percentage, 1 for 100%, 0.75, and so on. And these are the separate equations for working out the actual value of the resistors that we're going to need. This gets a little bit tedious doing all this. It's not that hard, it's just tedious. So I came up with a simpler way to do that. So I came up with this little spreadsheet to do it for me. So I want R1 to be 10K, it's a common value. And I've got the formulas put in here that you just saw on that other sheet I showed you. For 100%, we don't need a resistor. That's just a switch going straight through. But for 0.75, 0.5, and 0.25, the divider values using that formula worked out are 3.3, 10, and 30. And that would represent the total impedance of the resistor ladder on the top there. So if we look at the actual different resistor values for R2, R3, and R4, we get 3.3, 6.7, and 20K. And we're lucky there are standard values in the normal range where we can get those 3.3, 6.8, and 20K. So this gives a very, very small error here, and we can certainly live with that. Now, in this episode, I'm actually going to show you how I put together schematics on my EDA. My EDA happens to be dip trace. So I'm going to take you through that process, how I take a hand-drawn schematic or an idea, and I draw a schematic in dip trace, and then how we convert it to a PC board. But before I do that, let's get a word from our sponsor, PCBWay.
One of the really cool things about working with PCBWay is their complete clarity into the process that they have. So here's a board that I ordered yesterday, and I can go in and I can look at the production tracking on it. You can see every single step of the way. So these are all the main steps along the production line here. And if you have any questions about what each of these steps mean, you can go over here. You go to View Details, and it'll come up and it'll tell you exactly what each one of these steps is. Provides you information about the step, shows you what the step is like, and you can get further information about the process. Etching inner layers, drilling PCB, plating, it's quite phenomenal, the amount of information they share with you about what's going on with your boards. Once you start using PCBWay, your knowledge about PC boards is going to increase dramatically. It's basically 24 hours after the board is put in, it's then ready for shipping. So at this point now it's ready for delivery, and the next thing that will happen is the shipping department will send it off to me. Let's get back to our little project.
Okay, so here we are in dip trace. We're just going to lay out all the components, make sure that we select the components with the right footprint on them, and then lay them out, basically the way I had hand-drawn the schematic. So you can also do this right in the tool itself. You can build your schematic as you go along. I've done that before too. And lay everything out so it's a nice, easy to read schematic. You can understand it at a glance. And then we go and we set all the parameters around each of the components, their values, their names, how they're supposed to show up on the silk screen in the final PC board. And right here, we're going to actually build a label here for the connector that says SVG on it. We'll adjust that later, but we'll just get the basic components of that in there and tidy up a little bit and save this. And there we go. Now we're going to instruct it to create a PCB. Now it doesn't really create a PCB. All it does is really put the components in a random layout. And it's up to you then to take those components, rearrange them, put them in the way that you would physically like to see them in the final product. And of course, you have to kind of arrange them in a way that the traces underneath make some sense. So what I'll usually do is I'll take a first stab at the physical arrangement, and then I'll use the auto trace feature in DipTrace. And generally speaking, that's very unsatisfactory. So what I'll go in, I'll rationalize things. I'll move the components about, I'll move the traces about, so that it makes a more rational layout. And that's the process we're going through here. What I like to do, usually in small projects like this, is I like to put all the traces on one side so I can put a ground plane on the other side. Unfortunately, after much searching around here that you see me doing here, I was unable to get all the traces on the one side. So we'll dispense with the ground plane. Now we're looking here to size the board down. So we're going to try to compress in the traces as much as possible. We have to do this again later on. You'll see why. But to try and get the board down to a reasonable size. Adjust it here, adjust it there, try it, and see how it works out. Now I've got the board roughly the size I want, but I'd like to put some mounting holes in it. So we do that. I take the hole, I size them, and then they don't fit with the traces. So we're going to have to move things around a little bit. We're going to have to remove the traces. We're going to have to remove the components and resize the board in order to get the mounting holes to fit properly. And these aren't huge mounting holes. They're only, I think, 3 millimeters or something like that. But now we're going to go in and we're going to change that label for the SVG and how it appears here on the PC board. So we'll give it a first try. It's too close together. We're going to go out and spread it out in the schematic. Then we get it on the right side here, and we have to change that one capacitor there because I got the footprint wrong on that one. So there we go. Now any errors that came from the changes that we made, we correct for all those. We test it, we go through all the verification process, and then we save it and create the Gerber files. So that's what we're doing next here. We're going to tell it that we want to save all the Gerber files and the drill file. And that's basically it. Now we just have to wrap the thing up into a single file and send it off to PCBWay to be manufactured. So that's it, folks. That's all we have for you today. Thanks a lot for coming out, and we'll see you when these boards get back in. And thanks again to PCBWay for making all this possible. Bye-bye now.